Hello, Mr. Betts here. I want to take a look at a Lagrange error-bound example. But first, let's do a quick refresher of Maclaurin polynomials because we're going to need to look at the Maclaurin polynomial for sine of x here. So remember, a Maclaurin polynomial is going to be a polynomial that we use to approximate the sine function. And Maclaurin specifically means that we're centered at x equals 0. So what we can do here is we can take derivatives of f of x, plug in 0 to those derivatives, and we're going to use the formula for the nth term, which is the nth derivative evaluated at 0, because it's a Maclaurin polynomial, divided by n factorial times x minus a, remember a is 0, to the nth power. So that's going to give us the general term. And specifically with the sine of x function, the Maclaurin polynomial is going to be one that I am going to want you to be familiar with eventually if you're not yet. But sine of x is going to be approximately equal to x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, and so on. But since we're doing a fifth degree Maclaurin polynomial, we're going to be using that. So the first part here, we're not actually asked to do it, but we are going to have to know this for a later part. And that's the approximation that we get from this for sine of 0.1. So sine of 0.1 is going to be approximately equal to 0.1 minus 0.1 to the third power over 3 factorial plus 0.1 to the fifth power over 5 factorial. And this we're going to plug into a calculator. So when we plug that into a calculator, it doesn't say where to round it. So if we look at what we get from the calculator, we might round to 3 decimal places as the typical, or we might leave it as an exact answer. So an exact answer would be in the form that we have here, or some simplified fraction. So let me plug this into my calculator. And what we end up with is going to be about 0.0998333 and so on, more stuff here. So that's going to give us an approximation for the sine function at 0.1. We can also plug into a calculator sine of 0.1 and see how close this is. But the idea of the Lagrange error bound is we want to see how close this approximation has to be using calculus rather than using a calculator. So to use the Lagrange error bound, what we're going to consider is the largest possible value of the next term. So the next term is going to be the sixth degree term. So we want to know what is the maximum possible value of the sixth derivative of f evaluated at some point c, where c is going to be somewhere between 0 and 0.1. So 0 being the center because it's a Maclaurin polynomial, 0.1 being the point where we are evaluating the sine function. So it's the maximum possible value of the sixth derivative of sine evaluated at c times, this is going to be 0.1 to the sixth power. So we're plugging in the biggest possible value, or the value for x here that's going to give us the biggest possible value. So 0.1 to the sixth power over 6 factorial. And so let me mark this here. So this 0.1 to the sixth over 6 factorial, that's going to be positive, so I don't need absolute values. The sixth derivative of f of x, so the first derivative of f of x is going to be cosine of x. Then the second derivative is going to be negative sine of x. Then it's going to be negative cosine. Then it's going to be sine. Then it's going to be cosine. And the sixth derivative is really going to be the same as the second derivative, which is negative sine. Well, the biggest possible value of sine or cosine really is always going to be 1. So worst case scenario, when we're looking at the maximum possible value of a trig function, this is the maximum possible value of the opposite of the sine of x, somewhere between 0 and 0.1. Well, we know sine of x is always less than or equal to 1. However, with this particular function, remember the sine function looks like this, but we're talking about opposite of sine, which is going to look like this. At 0.1, the largest possible value is actually going to be bounded by negative 0.1, which absolute value is going to be positive 0.1. To justify that is a little bit complex. So what I'm going to do is I'm going to make it a simpler answer. And I'm just going to say this right here is bounded by 1. It can't be bigger than 1. Now, the reason I'm going to do that is because even assuming the biggest possible value here, which is bigger than we know it is going to be, 0.1 to the sixth power is 0.0000001, and then 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So this is a really, really small number because we're taking a really small number in the numerator and dividing it by a pretty big number, 6 factorial. And so we're going to get a really small number. So the maximum possible value of this, even assuming that this is going to be as big as 1, is going to be really, really small. So I'm going to go back to my calculator here. So in the calculator, we're going to have 0.1 to the sixth power divided by 6 factorial, and that's going to give us about 1.3, I'm going to just say 8 ... times 10 to the negative ninth power. So that's going to be 8 zeros followed by a 1. So what that means is this answer right here has to be within basically 1/1000th of the actual answer. So this approximation is really, really, really accurate. In fact, more accurate than the number of decimal places I wrote down. So I want to use my answer to determine an interval in which the actual value must be. I'm going to kind of cheat here, and I'm going to say this is equal to, let's say, k. So I know the actual answer, which is the sine of 0.1. That's what I'm trying to approximate here. So that actual answer is going to be somewhere between 0.99833 minus k. It's going to be less than or equal to sine of 0.1, which is going to be less than or equal to 0.99833, and so on, plus k. I kind of cheated a little bit here. This interval is so tiny that it doesn't really even make sense to talk about it as an interval. We can just say that this is a really accurate answer. Okay, second example is going to be one where, nope, not going to do another example.